So let's talk about the general concept of Mohr circles for 3D cases. I anticipate it will be 3D and 2D representations of the stresses. We already know that the stress state, which is a second order tensor symmetric, it can be diagonalized, and that means that there is a certain orientation of a system of coordinates for which this tensor is diagonal. So it just has components at the vertical, at the main diagonal, which are ordered from larger to smaller, defining axis directions then 1, 2, and 3 in that directions. So according to interpretation of the components, that means that in these particular planes, orthogonal to 1, 2, 3 directions, the stress state is just reflected by one tensile or compressive stress orthogonal to the plane. No tangential stress. Of course, this only happens for a very specific set of directions, but there is always this set of directions, okay? So let's assume that we know this set of directions. That's what Mohr did. So, and this is a state. So now let's assume that in this system of reference, we consider any other plane passing through the point with a certain normal n, and the corresponding traction vector is t, which is provided by the fundamental relationship of the stresses. The traction vector in a certain direction n is the product of the stress tensor, in these components this one, times the normal vector, which has the components n1, n2, and 3. So finally, the traction vector can be easily computed in that case as a vector having components sigma 1 and 1, sigma 2 and 2, sigma 3 and 3 in this system of coordinates. Okay? So that's true. Okay, now I want to compute the normal and tangent components of this vector. For finding the normal component, I just project t in the direction n. So I find that projection. And for doing that, we know that we just do the dot product of t times n. So the t that we have found, transposed, times against n, provides a result which is now in a scalar, which is sigma 1 and 1 square, sigma 2 and 2 square, sigma 3 and 2 and 3 square, which is sigma. This sigma also has sign. If sigma is positive, that means that this sigma has the sense of n. If this number is negative, that means that the sigma is against n. In the first case, if this is positive, we say that you have tension in English, not traction, tension. And otherwise we have compression, okay? So that's something that we can compute, and that is all. The normal tension or compression is this number here. Okay. Now let's look at the tangent component, and we are only concerned about the sign of that, so the modulus of that. So the modulus of that, of this vector, the modulus tau of this vector, can be computed according to the Pythagoras theorem as the modulus of t square equal to the modulus of this, which is sigma square, this sigma if I computed, plus tau square. So tau square could be computed as that minus this. Okay, so this is the equation to compute tau square. So, and from tau square, of course, I'm just concerned with the modulus, so just the square root of tau square, positive sign, is this tau understood as the modulus of tau n. So look that according to this, tau is always positive, but sigma can be positive and negative, right? So, from these equations, theoretically, I can compute sigma and I compute tau for any n. Okay? And now imagine that these are positive, sigma can be positive or negative. Imagine that I construct a space in which in this axis I have sigma, and in this axis, which is hidden by the label that, is tau. Okay? So sigma in the abscisses, tau in the ordinates. Okay? Look, for a given n, I do this operation. I know sigma 1, sigma 2, sigma 3, or whatever it is. I know the stresses, and I compute the sigma times n, and that is I compute t times n, and that's sigma, and I do this operation. and that's tau, okay? Of course, this can be done in this specific system of coordinates, but the same could be done in a specific system of coordinates. The numbers are simpler if I take the principal axes, the principal directions as coordinate axes, okay? But this can be computed in any case. And then I could represent, in this plane, the values of sigma and tau for n, and I will obtain 1 point, right? By the way, this point cannot be in the negative half space. Why? Because as I told you, tau is a positive number. So these points would be always in the positive half space here, but of course can be also in this side or in that side. Okay? So I could do that for one n. Now imagine that I want to compute in another n, and I obtain another point. I'll do that for another n, that's another point. So I would do, for every n, for every orientation of planes passing through the point that I'm studying, I could compute their representative point in the Mohr 3D problem half space, in the Mohr space. Okay? So the question is the following. Mohr asks himself, if I do that for all possible points, will I obtain, will I fill the half plane? So for every point of this space, infinite points, I have an orientation or not. I'm going to fill the full half space or not. What is the locus of the points that I would obtain, representing by sigma the normal stress and tau the modulus of tangential counterpart in that point? And that's the point that he wanted to ask. And that's an exercise that one can do really simply if one simplifies the equations by working in the principal axis directions. Okay? Look, the three equations that we have obtained are the following. The first one is that one that says that sigma equal sigma 1 and this one. This can be placed in form of equation this times this equal, this times this equals sigma. The second equation that you obtain is that. And again, you see that it's something that multiply n1 squared, n2 squared, and 3 squared equal sigma plus tau squared, and this can be placed in that equation here. And there is another equation that I could place here, which is, of course, n are normal vectors, normalized vectors, modulus 1, so n1 squared plus n2 squared plus n3 squared is equal to 1. So well, let's look at these three equations as a system of coordinates where the matrix of coefficients that I know, that's something I know, the principal stresses. These play the role of unknowns, x, and b something that I know. So my point is, given a sigma tau here, so sigma tau squared sigma, I know the independent term, and I know also the sigmas. The point is, what is x that I obtain? I can just, by solving this equation, I could obtain x. Look that this x cannot be any. So imagine that I obtain some x, sigma tau, some time x, that n1 is the first solution I obtain here, n1 squared I obtained it's minus 3. Can that be? N1 squared cannot be negative. So this couldn't be. The point that I place here, that inserted here sigma tau, provides 1 square smaller than 0, is not feasible. And what about an n1 squared equal 2? Can that be? Can that happen? No, because any component of n has to be smaller than 1 if the modulus of n is smaller than 1. So this point wouldn't fulfill that equation, of course. Okay? So that introduces the fact, looking at that not all points here, all imaginable points in this half space, Mohr space, half Mohr's circle space, not any point is feasible. So that not any point here corresponds to the counterpart of a given tractions in traction vector in a certain n plane defined by n passing through the point that we are studying. Okay, so now let's try to find out then what is the feasible, the locus that I would obtain if I just want to look for feasible values, so for values in the counterpart action, so given tractions obtain sigma and tau, okay? And this allows us to go into the system. This system can be rephrased just by some operations in that form, which is more suitable, 3 equations like that. This is a system of equations, okay? And now let's look to any of these equations, knowing that these equations are subjected to the restrictions that n1 squared is greater than 0 and smaller than 1, n2 squared is smaller than 0 and smaller than 1 and greater than 0, n3 squared is smaller than 1 and greater than 0. So let's look, for instance, to this third equation. For the time being, we disregard the first 2 equations, okay? This equation can be written in that way, that's the way we had it, but then it can be also written in that way. That's something that you can check very easily. Sigma minus a squared plus tau squared equal r squared. What does this equation looks like? A circle. A circle that here has no components, so it's a circle whose center is placed at tau equals 0. And the center is placed at point A0. That point C is A0, okay? And the radius, by the way, in that case, can be split in that way. So that's a circle. Look that, according to that, the center is fixed because it's 1/2 of sigma 1, sigma 2. Look, the center is at the mean point of the, what is this point here in the Mohr circle? The representative point of the plane at which sigma 1 acts. So if I wanted to represent in the Mohr circle that plane, the representative point of corresponding to this 1, okay? If I want, sorry, to this, there is a mistake here. It should be n1 here, and 2 here, and 3, okay. So to n1, if I want to, what is the normal component of the stress here? Sigma 1. What is the tangential component of the stress here? Tau, 0. So the representative points of these 3 planes are precisely, look, this representative of sigma 1, this representative of sigma 2, this representative of sigma 3. These are 3 points, which are feasible, because they correspond to real attractions points. And by the way, by construction, sigma 1 is more to the right than sigma 2, more to the right than sigma 3 by constructions, because sigma 1 are assumed to be greater than sigma 2 and greater than sigma 3. So, looking at that, the center of this circle is just sigma 1 plus sigma 2 divided by 2. So that means that is at the middle of these 2 points, okay? The upsize is C3, is at this point here, at the middle of these 2 points. And the radius, oh well, the radius can vary. It depends on how large is n3 squared. Looking that this value is positive, this value is positive, this value is positive by construction, so the smaller is n3, the smaller is the radius, the larger is n3, the larger is the radius, okay? So what is the smaller radius that I can get here? Well, the smaller value of n3 squared is 0. So for the n3 equals 0, I obtain one value here, which is 1/4 of sigma 1 minus sigma 2 squared, which is sigma 1 minus sigma 2 divided by 2. So there is a minimum circle with center C3, determined by this R3 minimal, and what is the maximum value that I can obtain in this expression for n3 squared equal to 1. So this provides another value which can be proven that the maximum value is 1/2 of sigma 1 plus sigma 2 minus sigma 3. So look, this is sigma 1 plus sigma 2 divided by 2 is that point, right? So this point, I subtract sigma 3, I obtain this distance, okay? So, okay, that means that all the possibilities I have here have to necessarily lie into that. There is no possibility fulfilling this equation, which is inside as this circle passing through sigma 1 and sigma 2 and center the midpoint of sigma 1, sigma 2, and larger than this radius here, so outside this region, which is defined by a circle, which is the same center, but a radius that passes through sigma 3. Follow me? Okay? So according to this equation, only equation 3, I have some limitations of the feasible points, points that correspond to actual n1 and 2 and 3, which fulfill the conditions, and 2 and 1 smaller than 0, smaller than 1, and 1 square smaller than 1 and greater than 0. So this equation says that this is the feasible region according to that equation. But of course we have other two equations, the 2 and the 1. Okay? And we could repeat the game. I just take the second equations, write that in that equation, and find what is the center and what is the maximum and minimum radius. And by doing that, we obtain the following equation. So the third equation is the one of the first that we obtain. The first center is placed at the midpoint of sigma 2 plus sigma 3, and the radius maximum is sigma 2 minus sigma 3, so it's a circle that passes through sigma 1, sigma 3, center that, and the other circle is, the maximum in that case, is just passing through sigma 1. Okay? So in other words, are two circles with the same center, one passing by sigma 1, sigma 2, sigma 3, and the third one passing through sigma 1. The second equation provides another center, which is at the midpoint of sigma 1, sigma 3, and the radius are placed at the other circles, passing through one circle, passing to the two principal stresses with this center, and the other circle passing from the other principal stress here, and that's the one that we have checked. Is the center is at midpoint of sigma 1, sigma 2, and the minimum radius defines a circle passing through sigma 1, sigma 2, and the maximum radius defines a circle which passes through sigma 3, right? So that's a simple geometrical analysis of three equations, very engineering, very simple. We don't need complicated algebra for that, just the equation of a circle. So let's summarize what are the feasible regions provided by that. This is the circles that we obtain. By center set C1, I just trace a circle which passes through sigma 2, sigma 3. This is sigma 1, this is sigma 2, sigma 3. Okay? So the center 1 pluses, one center pluses is placed at the midpoint sigma 1, sigma 2, and the circles are one passing by these two, and the other circle which is passes by sigma 1. But the second center is at the midpoint of sigma 1, sigma 3, and that is just the minimum and the maximum radius, and the third center is at the midpoint of sigma 2, sigma 3, and that's the minimum, and that's the maximum, and that's the minimum radius. So looking that there is no possible point placed outside any maximum radius and inside any minimum radius, which is the intersections of the feasible regions here. Well, one realizes that it is this section here, which is in gray, pattern, which is finally summarized in that. I have the 3 points representative of sigma 1, the plane where the first principal stress acts, which is that, sigma 1 tau equals 0. The plane where sigma 2, the second principal stress acts, which is normal stress sigma 1 tau 0, and that's the 3. Once I have that, constructing the feasible region is just constructing 3 half circles. So I could take the center on sigma 3, sigma 2, so 1 half circle passing by sigma 3, sigma 2, 1 half circle passing by sigma 3, sigma 1, and 1 half circles passing through sigma 3, sigma 1, that one. And the region inside this is the feasible region, the intersection of all possible regions that we call the feasible regions. So all representative points of the stress attractions in any plane passing through that point, don't forget that the starting point of that is sigma 1, the principal stresses, which in turn could be obtained by diagonalization of any stress state. So I have a stress state in a point, the stress tensor. I diagonalize the stress tensor. I obtain the three principal stresses, and I obtain the representative points in the Mohr's plane, and then I obtain the three circles, and all points in all other planes should be, the representative points in the Mohr's plane should stay in that state. There is no possibility for any point staying here and for any point staying here. Do you agree? By the way, look at this information. Tells, or this graphic construction. By the way, before going ahead, let me say that it can be proven that the opposite is also true. So all points in here, in turn, provide a solution for a direction, a unique solution for n1 square, n2 square, and 3 square that fulfills the previous conditions. So they are representative of a certain plane, the traction vector in a certain plane passing through the point. Okay? So finally, we found that this is very useful because all points are somehow, all tractions, possible tractions in all planes, are somehow represented by points here, and any points here are representative of a certain existing plane in the point. So questions can be now answered very fast at looking at that. For instance, what is the maximum normal stress acting in any plane passing through the point? What is the maximum sigma normal stress? Sigma 1. There is no possibility for any point having a normal stress greater than sigma 1. By the way, this can be proved also mathematically. Mathematicians also prove that and say that the maximum eigenvalue of a symmetric strength tensor is the maximum of all possible components of the in all directions. Okay, but the engineers found the same, but in a very simple way. What is the minimum value? The minimum value. Look, that this sigma 3 can also be in the negative side, right? Or sigma 2 or sigma 1. So we can just, the circle can be placed in the positive or in the negative side according to sigma. So the question is, what is the minimum value of sigma 3 in all planes? Minimum value of the normal stresses in all planes? Sigma 3. So if for any reason I get a computation and get a tau which is in modulus, larger tangential stress in modulus, that the half difference of the larger and the smaller principal stress, there is a mistake. It's not possible. Okay? So look, just look, a very simple look at these geometrical constructions provide a lot of information on it. Okay?